Welcome to the course Fundamental of Physics, GES 132 for Jubail Industrial College students. This is Shafiq Anwar, Health and Safety Consultant, Trainer, and your Physics lecturer. Today, we are going to start chapter number 13, Vibrations and Waves. If you look at the title slide of this chapter, you see a surfer is getting energy, from the ocean, wave energy, and he is utilizing it, to balance with the timing and balance. He's trying to do this adventure. So this is how we can utilize the waves and vibrations. So the topics we will be discussing: Hooke's law and simple harmonic motion, SHM we will call it. Then elastic potential energy. You remember you did in chapter number 5 potential energy. That was gravitational potential energy, mgy. Here, due to the springs, the elastic potential energy we will discuss in detail. And then you remember you finished already chapter number 7, circular motion. Today, simple harmonic motion, and we will compare these two. We'll see what are the similarities between these two types of motion. And then position as a function of time, how the waveform of the position changes with time and velocity and acceleration in the simple harmonic motion, how they depend on the position. And finally, another example of simple harmonic motion, that's the simple pendulum, we will discuss in detail. So first of all, Hooke's law. You see, if you have a string attached to a block of mass m, if I apply force on either side, say right now on the right side, I'll be increasing the length of this spring. If I compress it, I will be decreasing its length. So x is the change in the displacement of this mass spring system. Now, if I increase the force, I'll be increasing x displacement from the equilibrium position. So this is rest position, or we call it from now the equilibrium position. Okay, so this is equilibrium position. Now, when we have this concept that increasing force will increase the x and decreasing force will be decreasing x, so directly proportional relationship. So it means we have F is equal to K multiplied by x, the displacement. So this K is equal to, from this equation, force over displacement in the unit of Newton, force in Newton, x in meter. So this is the unit for K. K is called the spring constant. K. Okay? Now, once I apply the force, it extends. If I release it at that point, what will happen? Since I am doing work while I am stretching it or compressing it. So once I release it here, it will not stop. It will go back to its equilibrium position due to a force. We call it the restoring force. And keep in mind that this is the applied force in this direction, for example. A restoring force will be in the opposite direction. A restoring force in the opposite direction means it will be having, of course, opposite direction means negative sign will show. For example, if you have applied force equal to K multiplied by X, restoring force will be equal to what? Yes, minus Kx. This is the restoring force. Now, Fs is the restoring force, or we call it the spring force. This is the pushing or the pulling force of the spring at either side. So K is the spring constant. K is a measure of the stiffness of your spring. Large value of K mean a stiff, a strong, the spring. And the small value of K means a soft spring. Now, when we, this is X is the displacement of the object from the equilibrium position. For example, from here up to here, this is X. Now, this is the case of Hooke's law and restoring force. So, negative sign shows that the force is always directed opposite to the displacement, right? So, force and displacement in this equation, force and displacement in opposite directions, right? Okay. Now, because the displacement is on the right side, positive x-axis, so restoring forces along the negative x-axis. This is what we have this basic concept. Now, let's start simple harmonic motion. You remember we discussed in chapter number 2, translational motion or the linear motion, okay, along a single line, then in 2 dimensions. Then in chapter number 7 we discussed a circular motion when an object is moving around a circle about some fixed point. Now this is another type of motion. It's a special type of vibratory motion in which an object repeats its to and fro motion. To and fro mean from one point to the other about the equilibrium position. I will explain it. In equal intervals of time. So the object repeats its to and fro motion. For example, if you have spring horizontal to the right and the left, if you have horizontal about the equilibrium position, it will be repeating its motion up and down about the equilibrium position. So this is the simple harmonic motion. We assume at this stage, at your level, that there are no frictional forces. So in equal interval of time, it repeats its motion. The motion is caused by a force that is directly proportional to the displacement. This is what we call it the restoring force, and we just discussed this force that is like this one. Okay, I apply the force this side, it comes on this side. This is x is equal to 0, equilibrium position. This is x positive side, and once you reach here, you see, you release it here at this point, displacement positive, okay, and restoring forces x is positive, restoring forces negative on negative x-axis. Once the mass spring system reaches at x is equal to 0, it does not stop. Why? Because due to momentum and due to inertia, it will keep on to the left side with the same distance here, x. You see, once you are moving, and if you want to stop at one point, you cannot. Still, you are in momentum. You have inertia. So due to inertia, you will continue. The same is the case here. That once it is coming from this point towards the equilibrium position, it does not stop. Due to inertia, it goes to the other side along negative x-axis, right? So in this way, at this stage, once it reaches here, again the restoring force comes into action. So restoring force always tries to bring the mass spring system towards the equilibrium position. So now, since the x is negative, restoring force is positive along the positive direction here, Fs. You get the point? That's right. This is how we discuss force, restoring force and displacement. Directly proportional, of course, more x. Less force, less x. And a negative sign shows that yes, when you have x positive, restoring force is negative, like in this case. If you are here, displacement is positive. This is 0, this side is positive, this side is negative. So displacement is plus, so restoring force is along the negative direction. Once you reach here, x is negative, so restoring force along the positive x-axis direction. This is how we deal with these things. And these are some examples from the daily life. You might have seen the clock pendulum. This is its rest position, for example. It moves to the right side, comes back to the equilibrium position, does not stop due to inertia, it goes to the other side, and due to restoring force, at the two ends, it is, coming to the equilibrium position due to restoring force. And once it reaches here, it goes to this side or this side due to inertia. So these are the characteristics of the simple harmonic motion. Okay, that force and displacement are directly proportional, and acceleration also directly proportional to the displacement. All right. Now, okay. Now, you see, all right, some terminologies, another example, sorry, I forgot to discuss this one. So the shock absorber in your car, once you have bumpy road, there's a hole on the road, you go up and down. So the shock absorbers, they undergo simple harmonic motion, and you have smooth, the riding. Now, this is another example that the mass spring system, the same one we are discussing, that it is going, for example, these two are its extreme position, and this is the mid position. X is equal to 0. This is x minus, and this is x plus position. It goes between these two positions. This is what we discussed here. Okay. Now, some terminology which we'll be using in coming, discussion and examples. Right. Amplitude A. Right. Amplitude A mean if you have, for example, a spring attached to a block of mass m, it goes to this side and then this side. Okay, once you go there, the maximum position is called A, amplitude. Here you have minus A. Nothing new, the same thing we discussed, that if you have, now anywhere, this is the start in the middle equilibrium position, and this is your maximum displacement, maximum position from the equilibrium position. From the equilibrium position there, maximum, I can call it X max, maximum X, mean amplitude, A for amplitude. And on this side, you have minus X, okay, max, which is equal to minus A for amplitude. It's nothing, just simply we call it the maximum X is called from the equilibrium position, from here up to here, plus A, from here up to here, minus A. Amplitude is the same, only due to the direction we use this notation. Now, so this is an object in simple harmonic motion will oscillate between the positions X is equal to plus A and minus A. It will be moving like this one. Similarly, if you have a vertical mass spring system, it will be doing the same thing, by the way, like this one. This is X is equal to 0, this is X is equal to plus A, and this is equal to X is equal to minus A. Okay, like this one. So it will be rotating like this one. Then the time period T, capital T time period. The time, you see, your simple, your mass spring system, whether horizontal or vertical, it's performing simple harmonic motion about 2 points. Left side minus A, right side plus A. Up plus A, down minus A. So for example, if you start from this position, you go down and go back to the starting point. You completed one vibration, one trip or one cycle. How much time you take, that is called the time period capital T in the unit of second. Okay, right. You start from A, for example, to minus A and again to A. You start from A to minus A, again back to the starting point. One trip. The time taken for that trip, for that single vibration is called time period capital T. And how many vibrations, how many cycles you complete in 1 second, that is the frequency. Okay? The unit for the time period is second, and the unit for frequency is hertz. Right. Now, the acceleration of an object in simple harmonic motion. You see, the restoring force is given by minus kx, and also we have, according to Newton's second law of motion, F is equal to ma. Acceleration of an object in simple harmonic motion, A will be equal to this one. What is K? It's a constant, spring constant. What is m? The mass of the object. Again, it remains constant. So this term is constant. So what you get from here? You get a acceleration is directly proportional to minus x, because this is constant. What does it mean? Remember, you finished first force and displacement relationship 2 slides back. When you have displacement, for example, this side, displacement to the positive side, restoring force will be negative direction. If you are here, x is negative, restoring force will be along the positive direction. This is what you learned earlier. I just recall for your memory. Again, we have the same relationship because the force is directly proportional to acceleration. So force and acceleration have the same relationship with the displacement. Acceleration is directly proportional to displacement with the negative sign, means that if you have more and more larger value for the x, you have larger value for the acceleration. Negative sign shows that they are in the opposite direction, like the force. Okay, so we have, here, because this is the force, so from here you can get even A is equal to F over M. So this is the one relationship. This one and this one, by the way, the same, because the force is equal to, minus kx. So you can find out acceleration by this rule or by this rule. And the force, this one. So these two are the keys for coming examples. So F is equal to minus kx and A is equal to force over mass. So these two relationships you may need in coming examples. Again, this A is equal to force divided by the mass, right? And force is equal to minus kx. So you can use directly this value here also. It's okay, no problem. Okay, that's it. Now, let's have some more discussion for your better understanding. I know what's in your mind, and still we can chat once I upload it on the YouTube. You can leave your comments, your feedback. So don't hesitate to ask a question, and also guide me, suggest for me how other methods I can use for your better understanding. Because if you are sitting at home, for example, anytime, anywhere, you can communicate with me, inshallah. Alright. Hooke's law applied to a mass spring system. Again, as I told you, don't think that every time we'll be having horizontal mass spring system. You may have, the vertical, you can do it like vertical. So you might have done one experiment in the lab or on the online. Okay, let's focus on the force and the displacement. This is what I already discussed with you, again for your better understanding, my students. When x is positive, so this is the case. First of all, let's try to understand the whole pictures. Okay, this is a spring attached to a mass. Okay, this is restoring force. Okay, once you are here, x is positive. Keep in mind, this is x is equal to 0. This side you have positive x, this side you have negative x. Good. Now, you apply force, it reaches here. You're going to release it at this point, so it will go to the left. Due to what? Due to restoring force. Okay, now displacement, negative or positive? This is 0, this is plus side, so displacement is positive. Restoring force will be acting to the left, negative. Okay, once you reach here, what is the force? Force is 0. The question arises, once the force becomes 0 in the middle, how come it will go to the left? Good question. And the answer is, yes, it will, the force is 0, we fully agree, but still it will go to the left. How? Due to momentum and due to inertia. As I told you in the beginning, once you're running, and if you want to stop at one point, you cannot. Due to momentum, still you will cover some distance. This is what I'm explaining. Once you are riding, you are driving your car on the highway, and you have to stop momentarily, you cannot. Still you cover some distance due to inertia. So due to inertia, it will go to the other extreme position towards minus side. The same distance like here, x positive, x negative. So this is how you will be explaining it. So when x is negative, once you are here, it will be, x will be negative. When x is negative, restoring force will try to bring it to the equilibrium position to the right. Okay, let's use our knowledge now to solve first example. It's interesting, by the way, and right. So 0.350 kg, so this is the mass. Attached to spring of spring constant or the force constant, spring constant to the force constant, K in Newton per meter, is free to move on a frictionless horizontal surface as in the figure. If the object is released from rest at this position, find the force and the acceleration. Force and acceleration you have to find out. When at different positions. So first of all, at x is equal to this much. Now, as I told you in the last slide, so force is equal to minus kx. This is the restoring force, of course, and acceleration is equal to force over m according to Newton's second law of motion. How much k is given to you? 1.30 multiplied by x, this x. So you get the force in Newton 13. Okay, and acceleration is equal to force over m. Force is minus 13. M is equal to u. So you get acceleration minus 37.1. Can you notice one thing, please? You remember we did this thing. Any object with simple harmonic motion restoring force and the displacement are directly proportional and in opposite direction. Similarly, for acceleration and displacement. This is what you can notice here. X is positive, force will be negative. X is positive, acceleration is negative, and the vice versa. Any question? I would appreciate this. And similarly, you can do, keep in mind these two rules. This one for force and this one for acceleration. Use the x value and you can do the same. For example, I'm going to do, this is number 1, number 2, number 3. X equal to 0, force 0, acceleration 0. So 1, 2, 3. Let me do it the last one for 5. Okay? Number 5 at x is equal to minus this much meter. I use the same rule. Force is equal to kx with the negative sign, of course. Okay, and 1 point, how much k multiplied by x, how much x, minus 0 point. So you get the force minus and minus plus. So 13 Newton is your force and acceleration is equal to this rule. Force 13, the mass is equal to 37.1, sorry, meter per second square here. Meter per second square. Okay. You see, when x is negative, force will be positive. When x is negative, A will be positive. This is what you have to keep in mind. Right. So as I told you, you can do for any other values, whatever you are given, you can find out the basic rules. Force, this one, minus kx, and the acceleration, force over m. You may have any other correct formulas to do the same question, by the way. Now, next. Elastic potential energy. You see, you remember what we did in chapter number 5, that if you have an object and you take it from certain level to some height, what you are doing? You are doing work against the gravity. And once you leave it, it will do the same amount of work, the energy stored in it. So once I'm doing work in taking this above certain height, I'm doing work, and that work at this height is stored as potential energy gravitational. In chapter 5 you did. Now, potential energy, but from a different point of view. If you have a mass spring system, if you compress it or stretch it by applying some force, you are doing work. And that work is stored in the spring. For example, if I, stretch it up to here by applying force and then release it. Now at this point, the energy stored in it is called elastic potential energy or the spring potential energy. And if I release it here and you have some object here, it will do some work on that object equal to the same amount the energy stored in it. That is the elastic potential energy or the spring potential energy. So keep in mind that energy stored in a stretch or compressed spring is called elastic potential energy. Potential energy spring, S for spring or E for elastic. Some books you may find potential energy elastic or spring, half kx squared. What is k? Force constant or the spring constant. And what is x? X is the extension or compression. In the spring. Right? Right. So this is about elastic potential energy, and then you remember you did in chapter number 5 law of conservation of energy. In that chapter you discussed these two, kinetic energy half mv square plus mgy potential energy initial. Similarly here, kinetic energy half mv square final plus mgy final. So initial total energy is equal to final total energy. Now we are adding the spring or the elastic potential energy in it. So this is like this one, kinetic energy half m v I square mg half k x initial half m v f plus mgy final half k x squared final. This is the equation. So again, such equations, the formulas, they help us in solving different motion problems of different objects or the systems of the objects in physics. All right. Now, how energy can be transformed within this system, how the potential energy, spring potential energy is converted into kinetic energy and the vice versa. Let's have a look. You see, for example, a block on a frictionless surface collides with a live spring. So it's moving with the initial velocity vi. So the total energy of the system is half, this is the total energy, okay? As I told you in the previous slide, that this is the total energy. Initial is equal to total energy final, okay? This is initial, total, this is final, total. So what I am going to explain in the next slide is at every stage we will be calculating the total energy of the system. You see, a block is moving with the initial velocity vi. The spring is far away. There is no compression, no stretch in the spring. So elastic potential energy half kx square is 0 because x is 0 at this point, you see. And also this is on the horizontal